Hello guys. Today
So I think अलग है रोटेट डिवाइस म्हटलं
डिवाइस रोटेट करायचं
ते आलं लेक्चर पुढे चाललं
good morning students. Today we are going to study about the kinetic about the perfect black body. Now perfect black body. Yesterday we studied about the perfect black body, the body which absorbs total energy. This body is called as the perfect black body. Now coefficient of absorption of perfect black body is 1. Now, such type of perfect black body does not exist in a universe. Therefore, we are using the designed bodies which are called as the perfect black body. A Furious black body is the example of such type of body. Now, lamp black and platinum black, these are acts as the perfect black bodies. These are acts as the perfect black bodies. Now, it absorbs this artificial black body absorbs near about 97% energy. Now, what is the perfect black body? Actually, it absorbs the total energy. Coefficient of absorption is maximum, and for practical purposes, the black bodies are designed. Initially, we are studying about the Furious black body. The scientist Fury designed a black body. He designed a black body, and it is used as a perfect black body for the practical purposes. Now, what is the Furious black body? A Furious black body. Now, this is the diagram of Furious black body. Now, we can describe this Furious black body as it consists the double wall. It consists the double wall. Sphere. It consists the double wall sphere having a small aperture, or having a tiny hole which is called as the aperture. Now, outer surface is silver polished. While inner surface is coated with the lamp black. Now there are two walls. These are separated by a distance, and this space between the two walls is evacuated. Now rays of radiant heat enters through the aperture. Now inner surface has a thermal reflected back along the same axis. Therefore, there is a less chance of emitting this or returning this radiation through the small aperture. Now, when this ray enters through the aperture, and when it is incident on a conical projection, then these rays suffers multiple collisions. Therefore total energy is absorbed. Thus total energy is absorbed inside this sphere, and in this way we can absorb in this way, by using this Furious black body, we can absorb the total energy. Now, this small aperture, effective area of small aperture acts as the perfectly black body. This area of small aperture acts as the perfect black body. Now, listen again. Furious black body, it consists of double wall sphere having tiny hole or aperture. the incident radiation or heat enters through this aperture. Now outer surface is silver polished while inner surface is coated with a lamp black. Inner surface is coated with a lamp black. Also there is a conical projection on the inner surface. It is on the inner surface, and this conical projection ensures that the rays coming along the axis of aperture, not normally incident on the inner surface. These are not incident normally on the inner surface, so that these rays are not returning through this aperture. Thus, there is a less chance of returning this ray, incident ray, through this small aperture. And there, when ray enters through the aperture, it undergoes the multiple reflection. Inside this body, and thus there is an absorption of total energy by using this Ferris black body. Now this is information about the Ferris black body. Also, the scientist developed, or he designed the apparatus. He also designed the black body. But he designed the black body with the cylindrical body having the small aperture. Actually, in this case, we can draw such type of cylinder. But it consists the large area of the aperture. Means designed the black body. He took the cylinder instead of sphere. He took the cylinder having a vertical aperture, and this area actually it increases the effective area. Thus, this also acts as the perfect black body. Also, another body which is called as the cavity radiator. It is also acts as the perfect black body. It consists the block. Actually, it consists the block of material with cavity. It is called as the cavity radiator. Now, it consists the block of material with the cavity. There is a hole which connects this block and the cavity. It connects the both two surfaces, block surface and cavity. Now, when radiant energy is incident on this body, when heat is incident or when radiant energy is incident on this body, it enters through this hole. And therefore, when it enters through this hole, it enters in a cavity, and this energy cannot return through this cavity again, and this body acts as the perfect black body. Now, in this case, actually, when temperature of this body increases, or when temperature of a block increases, at that time it radiates the more energy, and this cavity acts as the perfect black body. Now, this radiation of heat is same as that of the perfect black body. This cavity radiates the energy. It is same, or it resembles the perfect radiation of perfect black body. Now, this radiation of heat depends upon the absolute temperature of this cavity. It depends upon the temperature of this cavity. When this block is heated, actually it radiates the heat. It radiates the heat or radiates the energy, and this radiation of energy depends upon the temperature of this cavity. It is not depend upon this shape and size of this cavity. Also, it is not depend upon this surface, but it depends upon the temperature of this cavity surface. This depends upon the temperature of this cavity surface. Just to remember that perfect black body, this Paris black body, it is as like this. Also, there are another bodies designed by the scientist. It is a cylindrical body. It is a cylindrical body having a large aperture. In this case, area of black body means this effective area is increased. Means in this case we get the large effective area of perfect black body. Now this is cavity radiator. It is also acts as its functioning is same as that of the perfect Paris black body or perfect black body. Actually, a block of material is there is a block of material. It consists the cavity. Inside it there is a cavity, and this cavity and surface of block is connected with a tiny hole. When incident energy when energy is incident or when heat is incident on this block, it enters through this aperture or tiny hole, and it is not returning from this cavity. When this block is heated, at that time it radiates the heat or it radiates the thermal energy, and this thermal energy is radiated by this cavity. It depends upon the temperature. It depends upon only the temperature. It is not depend upon the size and shape of this body or material of this body. Thus, this is about the perfect black body. Now, next point we are studying about the emission of radiation, emission of radiation or emission of heat radiation, emission of heat radiation. Now next point is emission of heat radiation. Actually, emission of heat radiation, we are studying emission of heat radiation. In this, we are defining the emissive power of body. Now this emissive power, already in perfect black body, you studied that this cavity radiator radiates the energy. It depends upon the temperature of cavity radiator or surface temperature of surface of cavity radiator. Now, emission of heat radiation. Actually, the scientist proposed. He published the theory of thermal radiation. He published the theory of thermal radiation. It is related with the theory of heat exchange. Theory of heat exchange. It means that when body is kept at any place, every body or all the bodies emits the energy or radiates the energy at all temperatures except the 0 Kelvin. Or in other words, we can say that all bodies radiates or emits energy at all temperatures above the 0 Kelvin. Only the body's temperature, when it is less than or 0 Kelvin, at that time it does not radiate or it is not radiating energy. But at all temperatures above the 0 Kelvin, all bodies radiates the energy. this energy is thermal energy, or we can say that radiant heat is emitted by the body. Also, at the same time, it absorbs the radiation energy or radiating energy from the surrounding. Also, there is a heat exchange of the bodies, heat exchange of body and surrounding. Just to remember that the scientist published the theory of thermal radiation, and it is related with the there is a heat exchange of heat exchange. This is the theory of heat exchange. Now, when body, all the bodies radiates the energy about all the bodies radiates the energy for all temperatures above the 0 Kelvin. At the same time, it absorbs the radiant energy from the surrounding also. If rate of radiation or if rate of emission is greater than the rate of absorption, means when absorbed radiated energy is more than the absorbed energy, at that time there is a loss of temperature. Or it lowers the temperature of body. Thus, actually, previous theory gives the heat exchange of body, and it depends upon the surface of the body. It depends upon the surface of the surface area of the body. Also, it depends upon the time for which this energy is emitted by the body. Also, it depends upon the this effective area, nature of the surface area. Means this radiation, thermal energy is radiated. It depends upon the temperature. Also, it depends upon the time, and it also depends upon the nature of the surface. Now, already we know when body absorbs the energy, its kinetic energy increases. Actually, atoms vibrate about their mean position with higher amplitude, and in this case, its kinetic energy increases. And we already learned kinetic energy is proportional to the absolute temperature. Means when energy is absorbed, its kinetic energy increases, therefore its temperature also increases. And then this body radiates energy. When it radiates energy, it means there is a loss of energy, and when it radiates energy, its temperature is lower, or it lowers the temperature of body. Thus, also we know when body radiates energy and absorbs energy, at the same time it absorbs the energy from the surrounding. If rate of radiation or rate of emission is same as that of the rate of absorption, means emitted energy is equivalent to the absorbed energy, at that time there is no change in the temperature of this body. Or temperature of body remains constant, and it is known as the thermal equilibrium. Then we can say that body is in thermal equilibrium with the surrounding. Now listen, when energy is absorbed by the body, there is a heat exchange between the body and surrounding. When this rate of absorption is same as that of the rate of radiation, in this case, temperature of body remains same or remains constant. It is called as this body is in thermal equilibrium with the surrounding. Means there is no change in the temperature of this body, but rate of emission is same as that of the rate of absorption. Now this is about the thermal equilibrium. Also, you already studied in 11th standard the example in cup of tea is placed in a room. When a cup of tea is placed in a room, also ice is placed. Ice or piece of ice is taken into a pot and it is placed in a room. At that time, we get this, in this case, this temperature of the tea. or temperature of the cup is greater than the room temperature. It is greater than the room temperature, and temperature of ice is less than the temperature of room. But after some, it is observed that temperature of this cup and temperature of ice is same. It means that there is a heat exchange between this tea cup and the surrounding. Also, there is a heat exchange between the ice and the surrounding room temperature. There is a room surrounding temperature. We are telling this as the room temperature, and after some time, there is a rate of rate of absorption is same as that of the rate of emission in both cases. In this case, we are saying these bodies are in equilibrium. These bodies are in thermal equilibrium. When there is a thermal, we are using word as the thermal equilibrium. There is no change in the temperature of the body. When these bodies gives the same temperature, it means that these both attain the same temperature. It means that these are in thermal equilibrium. Also, we know that when temperature of body is less than 800 degrees Celsius, 800 degrees Celsius, now this thermal heat is radiated, and wavelengths are longer. These wavelengths are longer than the visible light. Therefore, we cannot see this radiant heat. We cannot see this radiant heat because their wavelengths are longer than the visible light. And when temperature is approximately, when temperature is less than the 800 degrees Celsius, at that time body radiates the energy, and wavelength of this energy is longer than the visible light. Therefore, we cannot see or observe this heat or this radiant heat. But when temperature is near about 800 degrees Celsius, then this radiant heat is emitted, and this wavelengths of this radiant heats are shorter in visible range. These are in visible range. When temperature of body becomes 800 degrees Celsius, at that time we are observing the radiant heat in the form of red color. Means this body becomes red. It means that we are observing that radiant heat. It is red in color. And when this temperature is near about 300 degrees Celsius, or when this temperature is near about 3000 degrees Celsius, at that time this object becomes white hot. This object becomes white hot. Now all these examples shows that the quantity of radiant heat are there. This heat is radiated in the form of electromagnetic waves, and this quantity of radiant heat, it is represented by Q. It is this radiation of heat depends upon the absolute temperature. It depends upon the absolute temperature. Also, it depends upon the nature of body. Nature of body means nature of material. Also, nature of the surface of the body. And it also depends upon the area of the surface. It depends upon the area of surface, and it also depends on the duration of time. Or time for which this radiant energy is emitted from the body, or this thermal energy is emitted from the body. Time for which it is radiated or emitted from the body means this thermal energy is radiated from the body. It depends upon the absolute temperature. It depends upon the nature of the body. It also depends upon the surface area or area of the surface of body, and it also depends upon the time for which this radiant energy is emitted from the body. Therefore, also it gives the nature that this Q means radiant heat emitted by the body. Radiant heat emitted by the body, it depends upon the surface area. It depends upon the surface area of the body. Also, it depends upon the time. Also, it depends upon the time for which this energy is radiated. A time for which this energy is radiated. Therefore, for convenience, we can say that the radiant heat emitted per unit time, radiant heat emitted per unit time, per unit area, or per unit time, it is called as the emissive power of radiant power. It is called as the emissive power, and it is represented by R. Therefore, we get this emissive power or radiant power. It is equal to Q upon it. It is the radiant heat. It is the radiant heat emitted by the body per unit area, per unit time. It is called as the emissive power of body. It is called as the emissive power of body, or it is called as the radiant power. Now, from this we get this emissive power. Dimensions of this emissive power are L0 m1 t raised to minus 3. L0 m1 t raised to minus 3. These are the dimensions. Actually, this Q means what? Energy, heat energy. Now we know dimensions of heat energy are m1, L1, L2, t raised to minus 2. And dimensions of area are L2, L2. While this time is T, time is T. Now by taking this L2 means 2 minus 2, it becomes 0. And M1 is there as it is. And now this T raised to 1, it is taken at denominator. Actually it is T raised to minus 3. Therefore dimensions are L0 M1 T raised to minus 3. Now this radiant heat, actually it is measured in unit, and unit of this, actually this is the energy, it is measured in joule. Now it is joule per meter square. Joule per meter square. It is joule per meter square per second. Now this is the unit of this radiant power or emissive power. This is joule per meter square per second. But joule per joule per second is called as the watt. Therefore, it is equal to watt per meter square. Also, there is another unit, that is the watt per meter square. Now, this is the emissive power of the body, and emissive power of perfectly black body is maximum. Emissive power is maximum for the perfect black body because it absorbs more energy. That's why its emissive power is also maximum. Maximum emissive power. There is a maximum emissive power of the body, that is called as the perfect black body. Now this is about the emission of heat radiation. In this we are concentrating on the emissive power. Emissive power is equal to Q upon AT. This is the emissive power of ordinary body. In case of black body, we can write this as the RB. Now we are defining the coefficient of emission. Now, coefficient of emission, or it is called as the emissivity. Now, this emissivity is the ratio of two emissive powers. We know emissive power of the ordinary body or ordinary surface. Emissive power of surface, given surface, it is represented by R, and emissive power of black body is represented by, or emissive power of black surface is represented by RB. Now the ratio of emissive power, of given surface to the emissive power of black surface or perfect black surface, it is called as the coefficient of emission. Means now we are comparing the emissive power of different bodies. We are comparing the emissive power of different bodies. We are comparing generally emissive power of perfect black body is maximum, and we are comparing the any emissive power with the perfect black body, emissive power of perfect black body. Now this ratio of emissive power of the surface, ratio of emissive power of the surface to the ratio of emissive power of the surface to the emissive power of perfect black body. This ratio at the same temperature it is known as the emissive power. Therefore, E is equal to R upon RB. Actually, both are taken as both are the emissive powers at the same temperature. Now this is the we can define this coefficient of emission of a body, coefficient of emission of the given surface. Given surface is the ratio of emissive power of the surface, at a given temperature to the emissive power of the perfect black surface at the same temperature, and this ratio is called as the coefficient of emission. Now this coefficient of emission is maximum for the perfect black body. This E is 1 for perfect black body, and for reflector this E is equal to 0. For reflector E is equal to 0, and for ordinary body this coefficient of emission lies between the 0 and 1. It is greater than the 0 but less than the 1. This is the coefficient of emission or emissivity for the ordinary body. Also we know coefficient of emission for copper it is 0.3. Coefficient of emission for copper is 0.3. Thus this is about the emissive power. Now emissive power of polished surface is less, while emissive power of rough surface is larger. Emissive power of rough surface is larger. Thus this is about the coefficient of emission. Now we are going to obtain the relation between the coefficient of absorption and coefficient of emission, and it is given by the Kirchhoff's law. Now we are studying about the Kirchhoff's law of heat radiation. Now what is the Kirchhoff's law of heat radiation? Now Kirchhoff's law of heat radiation actually we are giving the proof of this Kirchhoff's law. Before that, what is the Kirchhoff's law? Now Kirchhoff's law, at a given temperature, we can state this as the at a given temperature the ratio of emissive power to the coefficient of absorption. The ratio of emissive power to the coefficient of absorption is equal to the emissive power of black body, at the same temperature for all wavelengths. At the same temperature for all wavelengths, it is known as the Kirchhoff's law of heat radiation. What is this? Actually, R upon E, that is the ratio of, at a given temperature, the ratio of this emissive power to the coefficient of absorption. Emissive power to the coefficient of absorption, it is equal to emissive power of black body at all temperatures at all wavelengths at the same temperature. Means when we are taking this ratio at a particular temperature, you have to take this radiation also at the same temperature. We can define this as the at a given temperature, the ratio of emissive power to the coefficient of absorption, it is equal to the emissive power of the black body at all the wavelengths. It is known as the Kirchhoff's law. Also, when body is in thermal equilibrium, and in case of body which absorbs and which radiates or emits, when body or for the body absorbing or emitting in thermal equilibrium, this coefficient of absorption, it is equal to emissivity. Coefficient of absorption of body, it is equal to coefficient of emission, or coefficient of absorption is equal to the emissivity. This is also the Kirchhoff's law of heat radiation. Just to remember that R upon E is equal to RB, or E is equal to E. This is the equations for Kirchhoff's law of heat radiation. Now, theoretically, these relations are proved by the thought experiment. Now, it is proved by the thought experiment. Now, what is the thought experiment? Thought experiment, we want to obtain this relation by using the thought experiment. Now, in thought experiment, consider the two bodies. First body is ordinary body, while other body is perfect black body. Two bodies are enclosed in a space. These are enclosed in a space. Now, actually, this ordinary body is A, while this perfect black body is B. Ordinary body is A, while perfect black body is B. Now, in this case, we are finding this relation A is equal to E. In the thought experiment, there are two bodies. Their area is same. These are the identical bodies. Means these are identical in geometrical shape. Now, Q is the radiant energy incident on this body. Q is the radiant energy or radiant heat incident on each body. This is same in case of both, because these two bodies are in thermal equilibrium. Therefore, there is no change in the temperature. Now, this is the same energy incident on ordinary body as well as perfectly black body. Now, this Q is the incident energy per unit time on this body, per unit area. Actually, this is the Q energy. It is incident on each body per unit time. Now, A is the area. Now, QA is the coefficient of absorption of ordinary body. This is the energy absorbed by the ordinary body. QA is the energy absorbed by the body. Now, A is the coefficient of absorption of ordinary body. Now, from this, actually, total energy is incident on this body is Q. Therefore, this energy absorbed by body, it is equal to A into Q. This energy absorbed by the body, it is equal to A into Q. We know this A is equal to QA upon Q. That's why this QA is equal to A into Q. This is the energy absorbed by the ordinary body, and rate of emission of this ordinary body is R. Emissive power is also the energy emitted by the body per unit time per unit area, and this is also the energy absorbed by the body per unit time per unit area. Therefore, we get this energy absorbed by the body, it is equivalent to the energy emitted by the body, and it is equal to AQ is equal to R. Now, energy incident on body B, it is also same. This is Q, and rate of emission of black body is RB. Therefore, energy which is absorbed, it is emitted. In this case, we get this Q is equal to RB. This is equation 1 and this is equation 2. Now, by dividing these two equations, we get AQ upon Q, it is equal to R upon RB. By cancelling this, we get this as the R upon A, it is equal to RB. But this R upon RB, it is equal to E. Therefore, from this equation, we get E is equal to E. And this is the proof of this Kirchhoff's law of heat radiation. That is, E is equal to E, or R upon A is equal to RB. And this is the proof of Kirchhoff's law by using the thought experiment. Next part we will discuss in next lecture.